All right, so we're moving into a new unit now on forces in motion. And as with most things in physics, there are some laws. These laws are going to govern or explain how motion happens and how forces can make motion happen. For forces in motion, we actually call those laws Newton's laws of motion, or Newton's three laws. And that's going to be after Sir Isaac Newton, who came up with these laws. He wrote about them in 1686. And even though he explained these laws hundreds of years ago, they have held true all this time. And the beauty of them is in their simplicity. That's not to say that they are all simple to understand, but we'll get into their complexity in class with some more challenging examples. The first law of motion is called the law of inertia. For those of you whom inertia is a new term, think of this as an object's tendency to just keep doing what it's doing. If it's at rest, it's going to stay at rest, and if it's moving, it's going to keep moving. The first law specifically states that an object in motion will remain in motion, and an object at rest will remain at rest unless it's acted on by another force. Now, what does that really mean? That means that something is going to stay still, or it's going to keep moving unless something else affects it, unless it's acted on by something else. Let me give you an example. Let's say that there are two balls of equal size, but one of them is a beach ball and one of them is a bowling ball. Now, common sense would tell you that if you set down the beach ball and rolled it, it's going to be a lot easier than trying to do the same thing with a bowling ball. Likewise, it would be a lot easier to stop a beach ball from rolling than a bowling ball. But why is that? See, this all has to do with mass, and inertia has everything to do with mass. And if the bowling ball has more mass, let's say 10 kilograms, and the beach ball only has 1 kilogram, we would say that the bowling ball has greater inertia. It has greater inertia. And we can say this because the bowling ball has more mass, right? It's going to be harder to get the bowling ball to move, and it's going to be harder to get the bowling ball to stop because it has more mass than the beach ball. But how do we get things moving at all? And that's where the second law comes into play. And the second law has everything to do with acceleration. Newton's second law is all about acceleration, which really is just going to be the rate of increase of speed, that is acceleration. The law is defined as the net force on an object is going to be equal to the mass times the acceleration. Now, the net force is going to be the sum of all of the forces acting on an object. And we can represent this with an equation. And it looks like this. Right? We have force, or the net force, is going to be equal to the mass of the object times the acceleration of the object. Right? F net is equal to m times a, or F equals ma. Here's an example. Imagine you have an ice rink, and let's say that there is no friction on this ice rink, meaning that if I push the puck, it's just going to keep moving forever. Now, at rest, the net force on this puck is going to be 0 because it's not moving, right? There isn't any force acting on it. All the forces are equal right now. It's not moving. It's actually in equilibrium. In this case, though, if I hit the puck, now the net force is not 0. Okay, I've exerted a force on it, which means that now there's going to be some kind of an acceleration. It's going to accelerate in that direction, in the direction that I hit it. And common sense would tell you that the harder I hit this, the more force that I hit this puck with, the faster it's going to accelerate. The interaction of the puck and the hockey stick brings up the last of the three laws, which is the law of reaction forces. And this is the one that you've probably heard of the most. It states that for every action, there is an equal but opposite reaction. And that opposite reaction is actually something that we call the normal force. It's the force that is acting opposite of one that is being applied. And so what does that look like? Right? You can actually do this yourself, for example, by pushing down on a table. Right? Now, when you push your finger down on the table, you are exerting a force, put this here, down on the table. The force of your finger is down on the table. But when you do that, the table is actually pushing back up on you. We know this because the table doesn't move. That means that both of these forces are equal. But that seems really weird, because if that's true, then how does anything move at all? If they always cancel out, shouldn't everything just stay still all the time? And that's a question that we're going to seek to answer in class. So there are 3 laws of motion that govern or explain how forces cause things to move. One deals with inertia. The second deals with acceleration, which we can represent by this equation here. And the last one deals with reaction forces. And we're going to get into more detail on each of these laws in class. And that is the end.